In this video, we're going to talk about variation of parameters. It's a very powerful tool, but you'll see that the process is quite lengthy, so we don't want to use this method when the other methods that we've already learned are available to us. But let's go ahead and get started. One of the things that you'll need to know for this that I didn't really talk about when we talked about linear dependence and independence is the Wronskian. It's covered in that section, and it is you're using determinants of matrices, but you're going to have functions inside of the matrix that you find the determinant of. For linear independence and dependence, we're seeing if that determinant is zero or non-zero. Here, we already know that we have a fundamental set of solutions when we get our solutions to our YC. So we're not worried about linear independence so much, but we need to know what that Wronskian is, and then we're going to make some changes to it, and that's going to help us find the functions that are going to be in our particular solution YP. Again, just follow along with the first few examples. I think that you'll get the hang of it. So starting with number one here, y double prime plus y is equal to secant of x. So we have our complementary solution, m squared plus 1. Our auxiliary equation, m squared plus 1 equals 0. So m squared is equal to -1, meaning that m is equal to plus or minus I, giving us a complementary solution of c1 cosine x plus c2 sine x. This part was c1 here, that's my y1. This part was c2 here is y2. So my yc, just so you understand, is c1 y1 plus c2 y2. These will be coming up later in the problem. So my Wronskian that I'm going to call W is, and it looks like absolute value signs, but it's the determinant of, and I'm going to put these y1 and y2 up here, cosine of x, sine of x. Then I'm going to take the determinant of each function, and I do that until I get a square matrix. I take enough determinants of the functions that I have until I get a square matrix. So since I have two columns, I'm going to have two rows here. The determinant of cosine is negative sine. The determinant of sine is cosine. Now, if you've never found determinants before, we're going to take this diagonal minus the product of this diagonal here minus the product of that diagonal there. So this is going to be cosine squared x, and then minus, and then this is going to be negative sine squared x. So that's going to be cosine squared x plus sine squared x. And we know by our Pythagorean identities that that's 1. So this is wonderful for when we are figuring things out later, because we're going to be dividing by this number. So we're only going to be dividing by 1 in this first problem. So now I'm going to take W sub 1, and what that's going to be is that I'm going to replace the first column with zeros everywhere above this function over here is going to be in my last row. So that's not going to look very interesting in a 2x2. If we had more functions, this would be harder, and I would have needed to explain more over here how to do that. I'm only going to do problems that are 2x2s right now. If your teacher wants you to do problems with 3x3s, I'll leave it to your teacher to show you how to do that. It's not that hard, but it's a longer process. Leave this other column alone, like that. So now we have the product along this main diagonal here is 0, minus the product here is going to be sine over cosine is tangent. So that's a negative tangent x. Now, for reasons that I just will tell you that to just do this. They explain it a little bit more in the book, but I'm going to take u1 prime and set it equal to w1 over w. This is my substitution that I want to make. So w1 is negative tangent x over w is 1. So my u1 prime is a negative tangent x, or I'm going to call that a negative sine x over cosine x. So if I want to find u1, I need to integrate this. It's a negative sine x over cosine x dx. So that's going to be ln of the absolute value of cosine x. Now I'm going to find w2, and I'm going to leave the first column alone, cosine x, negative sine x. Put my function in column 2 like that. Cosine times secant, they're reciprocals, so that's 1 minus 0, so that's 1. u2 prime is w2 over w. That's 1 over 1 is 1. So u2 is the integral of dx is x. So now I want my yp to be chosen as u1 y1 plus u2 y2. Now you see why we need to know what y1 and y2 were here. So this is going to be u1 was ln of absolute value cosine x, and y1 was cosine of x. And then we have x sine of x. So that gives me y c1 cosine x plus c2 sine x plus x sine x plus cosine x times ln of the absolute value of cosine x. And that is our first example, and we didn't see anything that looked close to that in our previous work. We couldn't deal with that secant x on the right hand side. We wouldn't have gotten anything that looked like cosine x times ln of cosine x and our undetermined coefficients. So there you have it. Now I am going to do a problem that we should have been able to do before, and you'll see that we should get the same answer that we got before. I'm just going to do it with the other method, and you're going to see why this method is longer and not necessarily preferred. So we're going to have our auxiliary equation here. So our yc equals c1 cosine x plus c2 sine x. I'll quickly go through the Wronskian again. It's the same Wronskian as before. And I won't go through all the work to show you that that's 1 again. So my w1 here is 0 sine x cosine x. And so that's going to give me 0 minus sine squared x is a negative sine squared x. So my u1 prime is negative sine squared x. So I need to have a negative integral sine squared x dx. Let's use my power reducing formula here. So that's 1 minus cosine 2x over 2 dx. For my, I should not have written the integration there. I should have written it on the next step. So this is equal to a negative 1/2 integral dx plus 1/2 integral of cosine 2x dx. I have a 2 and a 1/2. Gives me a negative 1/2 x plus 1/4 sine 2x. For reasons you'll understand in a little bit, I'm going to get rid of this double angle here just to make it easier for you to see things that will be like terms later. So I'm going to call that 1/2 sine x cosine x as we go along here. And then we have W2 is equal to, then we have 0 and sine x, and I have cosine x and negative sine x, and so this is sine x cosine x. So that makes U2 prime equal to W2 over W is equal to sine x cosine x. Really doesn't matter which way I go here. I'm going to differentiate so that the derivative of sine is cosine. So U2, the integral of sine x cosine x dx is going to turn into a 1/2 sine squared x. I'm going to alone for just a second, and so we have U1 y1 plus U2 y2 yp is U1, let's see, hang on a second. So this is U1 negative 1/2 x plus 1/2 sine x cosine x times y1, which was cosine x, plus U2 y2. All right, and we're going to have to ignore anything that's already in YC. So I get negative 1/2 x cosine x plus 1/2 sine x cosine squared x plus 1/2 sine x. I see a cosine squared, so I'm going to try and change these sine squareds into 1 minus cosine squared, just to see if anything zeroes out or combines here. So this is going to be negative 1/2 x cosine x plus 1/2 sine x cosine squared x plus 1/2 sine x minus 1/2 sine x cosine squared x. So plus 1/2 minus 1/2 zeros each other out. This 1/2 sine x gets absorbed into the YC, which has a generic C1 sine x term. So I don't need this one because it's already in YC. So my YP that I need to keep is -1/2 x cosine x, giving me a final total solution of C1 cosine x plus C2 sine x minus 1/2 x cosine x. As I said, that one would have been really easy to do with undetermined coefficients, either with the method of the superposition principle or the annihilator approach. I just wanted to show you there's another way. This is your method that for right now with linear equations with constant coefficients on the left-hand side, a linear differential equation. No matter what the right-hand side is right now, you know what to do. So very powerful, but kind of long. Let's look at another example here. Y double prime plus y is equal to cosine squared x on the right-hand side. M squared plus 1 equals 0. M squared equals -1. M equals plus or minus I. YC equals C1 cosine x plus C2 sine x. Wronskian is cosine x sine x negative sine x cosine x. We know that that's going to be equal to 1. Done that enough. So our W1 is equal to, this is going to be 0 cosine squared x sine x cosine x. So this is negative sine x cosine squared x. I'll just leave that as is for a second. U1 prime is going to be negative sine x cosine squared x over 1. So U1 is integral cosine squared x times negative sine x dx. It's going to be a 1/3 cosine cubed x. W2 is going to be, this is 0 cosine squared x cosine x negative sine x. So this is a cosine cubed x. Then we have U2 prime is cosine cubed x over 1. So U2 is integral of cosine cubed x dx. I'm going to save a cosine and change the cosine squared, 1 minus sine squared x dx. And U2 is going to be integral cosine x dx minus integral sine squared x cosine x dx. So this is going to be U2 is going to be sine x minus 1/3 sine cubed x. And then we want YP is U1 Y1 plus U2 Y2. So YP is going to be U1 is 1/3 cosine cubed x times cosine x plus a negative 1/3 sine cubed x times sine x. So YP is going to be 1/3 cosine to the 4th x minus 1/3 sine to the 4th x. And because these are both even powers, I could write them either in terms of sine squared or cosine squared. I'm actually going to just go ahead and do some factoring here though to help myself out. So this is going to be 1/3 and then cosine to the 4th x minus sine to the 4th x is 1/3 cosine squared plus sine squared times cosine squared minus sine squared. So that's going to be 1/3 of, and then that's 1, and that is cosine of 2x. So this is 1/3 cosine 2x. So let's see here. I also have a extra piece that I forgot about. Just a second, because there's this sine x that's up here. So that is u2, that's part of u2. So u2, y2 was sine. So there's another sine squared out here. So I can go ahead and say that this is let's power reduce that. So this is 1/3 cosine 2x plus 1 minus cosine 2x over 2. That just gets us kind of common things here. 1/3 cosine 2x plus 1/2 minus 1/2 cosine 2x. So we have 2/6 minus 3/6 is going to be -1/6 cosine of 2x plus 1/2. And that's my YP. That's the way that the book is going to write it. I just wanted to get you to the point where the book wrote it that way. So my total Y is equal to C1 cosine x plus C2 sine x plus 1/2 minus 1/6 cosine of 2x. I'll stop here and just call this part 1, and I'll come back and do some more examples in another video or two. I think this is really important that I get lots of examples, but I don't want to make the videos too long here, so I'll stop right there and we'll do some more examples next time. So see you next time for more variation of parameters.